Hello. In this lecture we'll talk about how to solve differential equations using Laplace transform. Let's talk about how we can use Laplace transform to solve differential equations. But before we go into the differential equations, we need a few basics. So, the first theorem that we need is the following. Laplace transform of derivative of a function is equal to s times Laplace transform of a function minus f of 0. And the second rule that we need is Laplace transform of the second derivative is equal to s times Laplace transform of the function minus s times f of 0 minus f prime of 0. Okay, so these two equations allow us to find the Laplace transform of a first derivative and the second derivative. And we're going to use this to solve differential equations. So let me illustrate with an example how you would go about solving a differential equation. Let's consider the following example. Y double prime minus y equals t, where y of 0 equals 1 and y prime of 0 also equals 1. Okay, so there are three major steps in solving a differential equation using the Laplace transform. The first step is to take Laplace transform of both sides of the differential equation. Okay, so this is your differential equation. We're going to take the Laplace transform of the left-hand side, and that is supposed to be equal to Laplace transform of the right-hand side. All right, now to take the Laplace transform of y double prime, we're going to use this formula. Okay? So instead of so imagine putting here y double prime. So then the transform of y double prime will be s squared times Laplace transform of y. So let me write this down here. S squared times Laplace transform of y. Well, we're going to just call Laplace transform of little y with capital Y minus s times y of 0 minus y prime of 0. Okay, so all I did is instead of f I used y, and then here when you have Laplace transform of little y, I denoted with capital Y. Okay, so maybe I should make a note here. This is just the transform of little y. Okay, we don't know what the transform of little y is. We just call it capital Y for now. All right, and then what else do we have here? Minus. So this was the transform of y double prime, and then we have minus transform of little y. Again, we don't know what the transform of little y is. We're going to just call it capital Y for now. Equals transform of t. So recall the transform of t is 1 over s squared. Okay, and let us replace y of 0 with 1 and y prime of 0 also with 1. And if we do that, we'll get s squared capital Y minus s times 1 minus 1 minus capital Y equals 1 over s squared. So that's our first step. We took the Laplace transform of both sides of the differential equation, and we obtained the following expression. Next step, we need to solve for capital Y. Okay? So to solve for capital Y, this is just algebra. What we do is we move all the terms with capital Y to the left side of the equation and all the terms without capital Y to the right side of the equation. So in our example, this doesn't have capital Y, this doesn't have capital Y, so we're going to move those terms to the right side. Okay? And we're left with s squared y minus y equals 1 over s squared. And if I move these two terms to the other side, they'll become s plus 1. Okay, and now I can factor out capital Y on the left-hand side. We'll get s squared minus 1 equals 1 over s squared plus s plus 1. And if we want capital Y, we just have to divide both sides of the equation by s squared minus 1. So divide this by s squared minus 1 and divide this by s squared minus 1. If we do that, s squared minus 1, s squared minus 1 cancel. And on the right-hand side, let me write it this way, 1 over s squared times s squared minus 1 plus s plus 1 divided by s squared minus 1. Okay, so this is the formula for capital Y. Capital Y equals that expression. So that was your second step. And the last step, once we have the formula for capital Y, to get back to the little y, we have to take inverse transform. So that would be your last step. So find little y, and you do that by taking the inverse of capital Y. So in our example, we have to take the inverse of 1 over s squared times s squared minus 1 plus s plus 1 over s squared minus 1. Okay, so to find the inverse transform, let me do a bit of algebra first. So I'm going to write this fraction as partial fractions, 1 over s squared minus 1 minus 1 over s squared. And you can check, if I subtract these two fractions, I'm going to get this fraction back. So this fraction equals these two fractions plus 1 over s minus 1. Okay, so how do I get s minus 1 here? Well, s squared minus 1 is equal to s plus 1 times s minus 1. So s plus 1 will cancel, and you get 1 over s minus 1. Okay, so maybe I should write this down. This factors as s minus 1 times s plus 1. So I'll cancel s plus 1s. All right, now we can take the Laplace, the inverse Laplace transform very easily. So to get the inverse transform of this term, we have to use the hyperbolic sign. And if you go back to the table that we had in the previous lecture and look at the table, you see that the transform of 1 over s squared minus 1 comes from sinh t. The inverse of 1 over s squared is t. And the inverse of 1 over s minus 1 is e to the t. Okay. So this is your y. This is your y, the solution of the differential equation. So this is an example of how you can use Laplace transform to solve a differential equation. And like I said, there are 3 steps. And anytime you have a differential equation that you want to use Laplace transform to solve, you go through those 3 steps. Before we look at the next example, we need a bit of a background. So one thing we need is the following theorem. This is the Laplace transform of the integral. So if I have the integral from 0 to t of little f tau d tau, then the transform equals 1 over s times capital F. All right? Now, the most common way to use this theorem is to compute the inverse transform. So in other words, if I have an expression that can be thought of as 1 over s times some function, then its inverse transform will be given by this integral. Okay, so let me show you an example of what I mean exactly. So let's say you're asked to find the inverse transform of 1 over s times s squared plus omega squared. All right? So what I want you to do is think of this expression as this. Okay? So how can I make it look like this? Well, let's rewrite it a little bit. Take out 1 over s and just write this. All right, so these are same. All I did is take out 1 over s. So now if I want to make this expression look like this form, then I would take capital F to be 1 over s squared plus omega squared. Okay, so I have 1 over s times capital F. If I want to find the inverse transform, I have to take the integral of little f, okay, to get the inverse transform. So it's the integral from 0 to t f of omega, little f of omega. Well, how can I find this little f? Little f is the inverse of big F. In our case, big F is 1 over s squared plus omega squared. So what's the inverse of this? Well, if you look in the table, you'd see it's going to be sine omega t, or in this case omega tau, divided by omega. Okay, so one more time, how do I get this? Well, in the formula it says little f is supposed to be the inverse of big F. In our example, this is our big F. So what would be the inverse of this? Well, the inverse of this expression is sine omega divided by omega. Okay? And now we have to integrate. We're not going to touch omega because omega is a constant. It's dividing by a constant. We're going to keep it. And what's the integral of sine omega tau? Well, we're doing it with respect to tau. So if you remember, the integral is minus 1 over omega cosine omega tau. So here I'm using the following formula. If you don't remember, the integral of sine kx dx is equal to minus 1 over k cosine kx. So this is the formula I'm using here. Instead of our k in this case is omega. So, and then this needs to be evaluated from 0 to t, 0 to t. 1 over omega divided by omega is 1 over omega squared. If I plug in t, I'll get cosine omega t. And if I plug in 0, I'll get 1. Okay. So that's our Laplace inverse. So let me discuss the idea of a unit step function. So we define our unit step function, this is ut minus a, as 0 for t less than a, and 1 for t greater than a. So this unit step function should be thought of as an on and off kind of a function. So you'll see what I mean by this if you look at the graph of the function. So here we have t, okay, and here we have 1, and suppose down here we have a. So the function u is going to be equal to 0 for t less than a. So for over here, for t less than a, the function equals 0. So the graph is going to be just a 0 graph. Then for t greater than a, the function is equal to 1. So this is how the graph would look like for t greater than a. Okay? So we have the graph of the function, of the step function. So it's sort of off until it reaches a, and then after a, it gets turned on. It's equal to 1. So it's a very useful function to describe any phenomena that involves sort of switching on and off. In particular, a lot of signals can be modeled mathematically using this function. So let me just quickly talk about the Laplace transform of the step function. Okay. So to find the Laplace transform of the function, we will use the original definition of the Laplace transform. So recall the original definition. It's the integral from 0 to infinity e to the st times the function. Okay? That's the original definition. Now, because the function is defined differently on different intervals, we have to break down the integral into those different intervals. So we're going to take the integral from 0 to a plus from a to infinity. Okay? So here we'll have e to the st times. Between 0 and a, the function u is equal to 0. And between a to infinity, the function u is equal to 1. So this whole integral becomes 0, and here we just have e to the st. And antiderivative of e to the st with respect to t would be 1 over s e to the st. And then we evaluate from a to infinity. And it seems like we're missing the negative sign. Okay. Now it's better. So if we plug in infinity instead of t, it's going to be e to the infinity, e to the minus infinity, which is 0. And then if we plug in a instead of t, we will get minus 1 over s times e to the minus as. So in the end, we get the following formula. The Laplace transform of the step function is equal to, minus minus is plus, it's equal to e to the minus as divided by s. Okay, so let's keep in mind this formula. Now let me do one quick example to illustrate how one can use the step functions. Okay, so let's say we have a signal whose graph looks like this. Okay, so think of this as a signal. I want to write the equation, the mathematical equation, to describe this signal, right? And so notice the signal. I think I need the zeros here. It consists of step functions, right? So let's use the step functions to write down the equation of this signal. So maybe you can take a minute and try to guess how can I write this signal as a combination of step functions. Okay, so let me now do this. Let's do this together. So let's define a function y equals 2 times u of t minus 1 minus 2 times u of t minus 4 plus u t minus 6. All right. Now let's think about why would this equation give you this graph. All right. Now, if I take, let's look at the interval from 0 to 1. 0 to 1. On the interval from 0 to 1, this function is 0, this function is 0, and this function is also 0. Remember, how do the step functions work? This step function is equal to 0 until 1. This function is 0 until 4. And this function is 0 until 6. So on this interval, they're all going to be 0. So you have 0 times 2, 0. So the combination gives you 0. Okay? Now let's think about the interval from 1 to 4. Now, from 1 to 4, this function now is equal to 1. This function is still 0, and this is also still 0. So what do we get? We get 1 minus 0 plus 0. That's equal to 1. And multiplied by 2, that gives us 2. So between 1 and 4, the function is 2. Okay, so it's working so far. What about between 4 and 6? Okay, this function is 1. This function now is also 1. And this function is 0. So we get 1 minus 2 times 1, which is minus 1, plus 0. So you get minus 1. Times 2 gives you minus 2. So we have minus 2 on the interval from 4 to 6. Finally, on the interval from 6 to plus infinity, this u is equal to 1, this u is equal to 1, and this u is also equal to 1. So we get 1 minus 2 times 1 plus 1. So that gives you 0. 0 times 2 is 0, so you get the 0 line. So we've shown that this signal can be described by this equation. Now that we have the equation for the signal, let's quickly find the Laplace transform of the signal. So the Laplace transform of the signal would be the following. So we have 2 times. What's the Laplace transform of u of t minus 1? Well, let's use this formula. Here a is equal to minus 1. And so put minus 1 in here, and you get e to the minus s over s. And then we have 2 times the transform of this. Again, use the same formula, a equals 4. And then, again, use the same formula for the last term. So here is the Laplace transform of this signal. All right. Now, one last thing that we need before doing our big example. It's a theorem called T-shift. So this T-shift says if I have the transform of f of t minus a times u t minus a, this is equal to e to the minus as times capital F. So this equation is what we call T-shift. It stands for time shift. So the most common way that people use this equation is to find inverse transforms. If I have an expression of this form, e to the minus as times some function big F, and I want to find the inverse transform of this, it's given by little ft minus a times ut minus a. Okay? So we're going to use this to find inverse transforms. Let me do a couple of quick examples. For example, let's say I want to find the inverse transform of e to the minus s divided by s squared plus pi squared. Okay. So it seems like I have e to the minus s. So maybe I can try to use this equation, right? If I want to try to use this equation, I have to write my expression in this form. So let me just write it a little bit differently. Let's write it as e to the s times 1 over s squared plus pi squared. So now it's very clear to see what's going on. If I want to think of this expression in this form, then a would be equal to 1, and capital F would be equal to 1 over s squared plus pi squared. Okay, so that's what we have. Now if I want to find the inverse transform will be given by this formula. It's going to be little f t minus a. Well, a we said is equal to 1. U of t minus a. A is 1. Now, what we have to do is find little f. Okay? So little f is the inverse of big F. Little f is the inverse of big F. In our case, this is our big F, we said, right? And what's the inverse of this expression? It's sine pi t divided by pi. Okay? So if this is f of t minus 1 would mean just replace t with t minus 1. And we'll get sine of pi times t minus 1 divided by pi times u of t minus 1. So that's our inverse transform. Let me do one more example. Okay, perhaps you can take a second and try to find the inverse transform using the T-shift on your own. See if you can do it. Okay, let's try it together. Again, we suspect that we might be able to use the T-shift formula to find the inverse transform. So first let's make it look like the T-shift formula. So I'm going to write it as e to the minus 3s times 1 over s plus 2 squared. Okay, so here it's clear a would be 3, and big F is equal to 1 over s plus 2 squared. So then the inverse transform is going to be f t minus 3 times u t minus 3. Okay. Now let's find little f of t. We find little f of t, and then we're going to plug it in here. So little f is the transform of big F, and our big F is, we said, this expression. So what's the inverse of this? Well, this function looks kind of like 1 over s squared, right? But it's shifted by minus 2. So we have to use the s shift formula. So 1 over s squared comes from t. And here, because it's shifted by minus 2, we're going to get e to the minus 2t times t. Okay, so go back to the other lecture and review the s shifts. So we use s shift to find this inverse transform. Okay, so now that we have little f, to find little f of t minus 3, all I have to do is replace t with t minus 3, and we'll get e 2 times t minus 3 times t minus 3, and then the step function. So that's our inverse transform. Okay, so now we're finally ready for our big example. We will talk about finding the current in an RC circuit. All right, so imagine we have an RC circuit with a constant capacitance and a constant resistance. So C and R are some constants. And we have a voltage. Okay? Now the voltage is not is not constant. The voltage is given by this function. So our voltage is 0 until time t equals a. Then the voltage becomes V naught. So V naught is some constant. So imagine maybe this is 3 volts. So you give a constant voltage between A and B. And then after B, the voltage becomes 0 again. Okay? So in this situation, we would like to find the current in the circuit. Now, it's known from physics or maybe electric circuit that the current in the circuit must satisfy the following equation. So the current in the circuit must satisfy this equation, and if we solve this equation, we will find the current. And this is called an integral differential equation. So it's a differential equation, but it has the integral inside. But we're going to think of it as a regular differential equation. So, and we're going to use Laplace transform to solve this differential equation. Now, if you remember the steps for Laplace transform, the first thing we had to do is to take Laplace transform on both sides of the differential equation. So let's do that. If I take the Laplace transform of this term, I'm going to get r, which is a constant, times the transform of little I. Well, we don't know what the transform of little I is, so we're just going to call it capital I for now, plus 1 over c times the transform of this integral. Now, if you go back in this lecture and look at the formula for the transform of the integral, it was equal to 1 over s times the transform of little I. Again, we don't know what the transform of little I is. For now, we're just going to call it capital I, equals the transform of the voltage function. Well, to get the transform of the voltage function, let's write this signal as a combination of step functions. So if I take ut minus a minus u of t minus b, and I believe this formula will describe our signal. So let's think about how it's going to work. On the interval from 0 to a, this function is 0 and this function is also 0, so 0 minus 0 gives you 0. Okay? Between a and b, this function now is equal to 1. This function is still 0. So we have 1 minus 0 times v naught. That gives you v naught. Beyond b, this function is 1. Now this function also becomes 1 after b. So we have 1 minus 1. That's 0. So we have the 0 signal. All right, so this is the formula for the voltage. And what I want to do in our differential equation is to take the transform of this voltage function. So to take the transform of the voltage function, I'm going to use the formula for the transform of a step function. So if you remember, the transform of this would be e to the minus as over s, and the transform of this would be e to the minus bs over s. So that's using one of our formulas. So what we get is v naught times e to the minus as divided by s minus e to the minus bs divided by s. That's our transform. So this was our first step. Get rid of this. The next step was to solve for capital I. Solve for capital I. So we're going to keep all the terms with capital I on the left-hand side, and all the terms without capital I, we move them to the right-hand side of the equation. Well, here, this term has capital I, this term has capital I, so they will stay on the left-hand side. And none of these terms have capital I, so they will stay on the right-hand side. So we don't really have to move anything in here. All we're going to do now is to just factor out I. So if I factor out I, I'm going to get capital R plus 1 over CS. Okay? And this is equal to V naught e to the minus as over s. So from here, I can solve for capital I. Capital I is equal to, so what do we have to do? We have to divide by R plus 1 over CS. Let me take out this S, and I'll have V naught divided by S divided by R plus 1 over CS. e to the minus as minus bs. Okay? So that's what we have. That's our second step. And now the last step, we want to find the little I, the current, and we do that by taking the inverse transform of big I. So third step, we need to find little I, our current. We'll do that by taking the inverse of big I. So let's take the inverse of this big I expression. Let me simplify this expression a little bit. Let's multiply by s the top and the bottom of this fraction. So if I multiply the top by s, this s will go away. If I multiply the bottom by s, I'll get r times s. And here s will cancel and I'll get just 1 over c. And the rest. Okay? Is this enough? I think we need to make one more small change. Let us do one more simplification. Let's divide the top and the bottom of this fraction by r. Okay, so divide the top by r. We'll get v naught divided by r. Divide the bottom by r. We'll get s plus 1 over rc. Okay, dividing everything by r. Times our exponentials. Now, let me split this into two parts so you can see clearly what's going on. So I have v naught divided by r, s plus 1 over rc times e to the minus as and minus v naught over r s plus 1 over rc. Okay, so we're going to find the inverse transform of each part separately. But you see they're basically the same. So once you figure out how to take the inverse transform of this expression, the other expression will be 99% the same. So how can I find the inverse of this expression? Well, remember the formula where we had e to the minus as times capital F, and we wanted to find the inverse. I'll write down that formula down here for your convenience. This is for t shift. F of t minus a times u t minus a was equal to e to the minus as times capital F. This is the t shift formula. So anytime you have an exponential times some function and you want to find the inverse of this, you can use this formula. And that's what we have here. That's what we have here. We have our exponential and we have our big F. So we're going to use the t-shift formula. And here a is equal to a. So let us continue down here. Let me just take the inverse of this part. Okay, forget about this part for a second. Let's just concentrate on this part. So the inverse of this, using the t-shift formula, would be f of t minus a times u t minus a. Now we need to find what's little f, and then we plug it in here. Well, little f will come from big F. In our example, this is our big F. And if you think about it for a second, you see that the inverse transform of this expression is v naught divided by r e to the minus 1 over rc t. Okay, because really this, I mean, rc is a constant, so think of it as s plus a constant. If you go back, look at the table, it will make sense. So now, to get f of t minus a, I have to replace t with t minus a, and I'll get v naught r e to the minus rc t minus a. So that's our inverse transform times, of course, the step function. Right. And we will find the inverse transform of the second term in exactly the same way. We're going to use the t-shift. So now let me write down the final answer. So the final answer would be the transform of the first part, which we have over here. I'll just copy it. V naught r e to the minus 1 over rc t minus a u t minus a minus the transform of the second part, again using the t-shift, v naught over r e to the minus rc t minus b u t minus b. Okay, so that's our final answer. So if you think about it, the current will be 0 until t equals a, because this part is 0 and this part would be 0 until a. So the whole thing will be 0. Between a and b, this part now will be equal to 1. So it will be 1 times this exponential function. This function will still be 0. So between a and b, you'll just get this function. And then after b, you get a combination of the two functions. So that's the final answer. And we're done.